playing with YouTube. So if you could.
Actually, I can't because I'm not co-host at the moment.
Sorry.
I can admit everybody if that's what you want.
Okay. Good. So I think everyone is in now. Everyone who wanted to come. So hello again. Okay. And Shayan will. Oops. Now we are getting terrible feedback. And Shayan will continue with his third lecture on polynomials. Please, Shayan.
Sure. Hello, everyone. Welcome back. So the topic of this lecture is max entropy convex programs and applications to traveling salesman problem. Now, before getting to that, I just wanted to prove one last lemma I didn't get time to do in the last lecture. So remember, we wanted to prove the base case of the Gurwitz machinery, Gurwitz theorem, which is that if you have a univariate polynomial with non-negative coefficients, which is real rooted, then the basically this inequality holds 1 over e infimum of t less than t more than 0 f of t over t is less than or equal to f prime of 0. So just to let you how, I mean, the way you should think about this, what is f prime of 0? F prime of 0 is basically the coefficient of t in the t in this monomial. And what we're doing here is that we're saying you can approximate the coefficient of t by looking at this ratio of f of t over t and take the minimum possible value over all t's. Okay, so let's see how to do that. The main idea is to use log concavity of f. So here is the fact that log of f is concave over non-negative reals. And the reason to see that is the following. Because f is a real rooted polynomial, I can write f as product of t plus alpha i's, where alpha i's are non-negative. Why is that the case? Here, I'm crucially using that f has non-negative coefficients. Now, if you have a real rooted polynomial with non-negative coefficients, then all of the roots must be negative. You cannot have positive roots. So since all of the roots are negative, you get alpha i's here positive, because normally you would write a polynomial as product of t minus alpha I, t minus the roots. Here, these alpha i's are negative of the roots. That's why how you can write f this way. Okay. So you have this form. Now, what is log of f? Log of f is equal to summation of log of t plus alpha I. Now, one test to see if a polynomial is concave, if a function is concave, is to take the second derivative. So here we do that. If you take the second derivative of log of f, it's basically equal to summation of minus 1 over t plus alpha I squared. Basically, the point is we know log is a concave function, and here we have summation of logs, which is also concave. Okay, so that's the proof of the fact. Now, using this, we want to prove the lemma above. Again, that you have a real rooted polynomial. Now, I just want to assume that it is log concave, and I want to prove that inequality. Now, the main observation here is the following. You may have seen this in your convex programming course, for example, that if you have a concave function, it would look like this. Now, if I have a point here, x, I look at the tangent line at x, my diagram of my function sits below this tangent line. So as a consequence, what I get is that if I look at the point y further ahead, f of y is less than or equal to f of x plus f prime of x, which is the slope of the tangent line, times y minus x. Okay, so this is the inequality which holds for any concave function. And we're going to use it here. So in our application, log of f is a concave function. So I get that log of f at t is less than or equal to, so y will be t in my application, and x will be 0. So it would be less than or equal to log of f at 0 plus f prime of 0 times t. Sorry, not f prime, log of f prime. Log of f prime at 0 times t. Okay, so okay, so in other words, this guy is nothing but f prime of 0 over f of 0 times t. Okay, so I get this inequality out of everything I said. Now, one last thing is that, so I'm interested in f of t over t. So let's just look at that object. So if I look at log of f of t over t, it's less than or equal to log of f of 0 plus f prime of 0 over f of 0 times t minus log of t. Basically, I'm subtracting log of t from both sides of this inequality. So I have this. Now I know that this must hold for every t, every non-negative t, real number t. So in particular, if I optimize for t in the right-hand side, if I choose the minimum possible value for t in the right-hand side, or any possible value for t in the right-hand side, the same inequality should hold for every t that I choose in the left-hand side. So for the right-hand side, you take the derivative and you set that set t to be f of 0 over f prime of 0 in the right-hand side, and basically you get what you want. You get that log of infimum of log of f of t over t is less than or equal to log of f of 0 plus 1 minus log of f of 0 over f prime of 0. Now f of 0 cancels out, so this is equal to, sorry. This is equal to 1 plus log of f prime of 0, which is exactly what we want. It's log of the inequality that we wanted to prove. Okay, so just one lesson I wanted to tell you from this calculation is that there are many applications, there are many statements in this field of geometry of polynomials where when you want to prove it, you better look at the log of your generating polynomial, okay? Not the actual polynomial. The derivatives of the log work out very nicely in many applications. They also show up very nicely in applications to Cadison-Singer problem, even though we don't cover it here. So, oh, and again, just to remind you, last time as I said last time, here we proved that any real-rooted polynomial is log concave. Real estate polynomials again inherit this property. So any real estate polynomial with non-negative coefficient is also log concave over the non-negative ortho. And one last thing, so this is this base case of the induction, again, as I said last time, is the main property of real estate polynomials that we use in this proof. Basically, the whole proof of Oveis is the closure under differentiation and assigning real numbers. And basically, you just want a class of polynomials which are, after assigning real numbers or differentiation, whenever you get to a real-rooted polynomial, whenever you get to a univariate polynomial, it is log concave. That's all you need, and that's why the machinery generalizes beyond real stability. It goes to mixed volume and so on. Okay, so that's all I wanted to say. Now let me go to this lecture. Is there any question? So so now let me, so as I said, this lecture is about max entropy convex program and application to TSP. So in the last lecture, we talked about this program, infimum of P of Z over Z1 up to Zn, where Z is positive. In this lecture, we sort of generalize this. I talk about, so I call this program max entropy program. Which is infimum of, again, Z positive over P of Z over Z to the alpha. Now, what is alpha? Alpha is some vector in non-negative reals. And again, remember, Z to the alpha is just product of Zi to the alpha. Okay. Now, this program I wrote here is not really convex. So again, you can convexify it using the trick we talked about last time. So the convex version of it, which gives you the same sort of value, is that you maximize over all vectors y, p of e to the y1 up to e to the yn over e to the y dot product alpha, take the log of it. Okay, so this is the convex version of the same program. So you basically want to talk about this program in this lecture, study its properties and its applications. Okay. So again, the connection to the program we talked about last time is that the last time alpha was the all ones vector. Here it's not. Okay. So let's get started. The first thing I want to tell you is I need a definition called an object you may have heard about. It's called Newton polytope. Okay, so let's say you have a polynomial p of z. Let's say I write it this way. I write it as summation of cp of kappa z to the kappa, and kappa is in z non-negative. Okay, so this is basically I write cp of kappa to denote the coefficient of z to the kappa in this polynomial. So the support of this polynomial are basically all kappas for which cp of kappa is positive, or is, sorry, non-zero. Then the Newton polytope of P is basically the convex hull of all vectors kappa in non-negative reals, such that the coefficient of kappa in P is non-zero. Okay, so one example, if my polynomial P, let's say it's equal to z1 squared plus z2 squared, then I can draw it very easily. I have I need a two-dimensional space R2, and then I have, so this monomial gives me the point 2, 0. This monomial gives me the point 0, 2. So I look at 2, 0, which is this point, and 0, 2, which is the other point. And then I take the convex hull of these two, which in this case would just be a line. Okay. So one thing to notice is that there is an integer point in this polytope, the point 1, 1. It is in the 1, 1 is in the Newton polytope of this polynomial, but it's not. It doesn't have a positive coefficient. Okay. In the polynomial. Okay. Any question about Newton polytope? Okay. Now, let me tell you a lemma. Okay, so let's say you have a polynomial P, again with non-negative coefficients on n variables, and let's say alpha is in Rn, again non-negative, then infimum of z positive of p of z over z to the alpha is more than 0, note that this is never negative because p of z is always non-negative and z to the alpha is always non-negative. It's either 0 or more than 0. So it's more than 0 if and only if alpha is in the Newton polytope of p. Okay, so all I'm saying is that if you have any points inside the Newton polytope, this thing would be positive. Otherwise, it will be 0. Okay. Now, so for example, one application or one example is that in the last lecture, we were talking about this, the infimum of pz over z1 up to zn, basically, when alpha is 1, right? So this lemma says that if this thing is positive, this infimum is positive, then the point 1, 1, 1, 1, 1 is in the Newton polytope of P. Okay, and what Gurwitz's theorem says is that basically this 1, 1, 1, 1. So this is if and only if, and okay, so let me actually write it on the other side. What Gurwitz's theorem said was that this thing is positive if and only if Cp of 1, 1, 1, 1, 1 is positive. Okay, if P is real stable. So basically, if you put these two together, you see that. So this is Gurwitz's theorem. It says that a point 1, 1, 1, 1 is in the Newton polytope of my real stable polynomial P if and only if the coefficient of 1, 1, 1, 1 is positive. Now, this 1, 1, 1, 1 is not a special case. In fact, you can use the same machinery of Gurwitz to say that this is true for any point. So it's true for any alpha. Sorry, any alpha in, Zn. So in general, if you look at any integer point in the Newton polytope of a real stable polynomial, it has non-negative coefficient in the polynomial. That's a special property of real stable polynomials. Okay, so more generally, for any integer point in Newton polytope of P, point, let's say kappa, Cp of kappa is positive. Okay, so this is a special property of if P is real stable. Okay, so you see here a difference between this statement and the example we saw above, z1 squared plus z2 squared. That polynomial, as we said before, is not real stable and it doesn't have this property. You see a point 1, 1, which is in the Newton polytope, but it has coefficient 0. Okay, so this fact is fairly general. Like if you remember in the first lecture, we said that if you have a real stable, if you have a homogeneous multi-affine real stable polynomial, the support corresponds to basis of a matroid. It corresponds from this fact again. Basically, the point is if you have a homogeneous multi-affine real stable polynomial, the Newton polytope of this polynomial should exactly be the so-called matroid polytope, matroid-based polytope for a matroid M. And the reason that it must be a matroid follows from the same thing. Basically, if it is not coming from a matroid, you would get integer points in the Newton polytope, and that's a contradiction. Okay, so that's what I wanted to say about applications of this lemma. Now so this is a if and only if lemma. I haven't proved the lemma yet, so let me prove. Okay, so there is a question. there are two if and only if from. Yes, exactly. Yes, this one holds for all. The top one holds for all. The other one holds for real stable. Exactly. That's true. Yes. The lemma I've written here, it doesn't need any assumption for the polynomial P. Thanks for clarification. Good. So okay. So I'm going to prove one direction of the lemma. The other direction you can read it from the notes. So let me prove. So I proved that if alpha is not in the Newton polytope of P, then this infimum of Pz over z to the alpha is 0. Just to give you a flavor of how such an argument could go. So the way you do it is the following. So let's say you say this is a Newton polytope, and it's a convex object, and this is my alpha. And if alpha is not in the polytope, there is a separating hyperplane. So it means that there is this vector c, so there exists c such that c times alpha, c dot product alpha, is basically more than dot product of every point in the Newton polytope. So let's say c times alpha is at least b plus epsilon for some real number b, and c times z, c times, let's say, let's say c times x is less than or equal to b for all x in the Newton polytope. Okay, so that's what you get from the separating hyperplane. Now, I want to say that this infimum is 0. So I want to plug in a sequence of values for z such that, as the sequence goes to infinity, this infimum goes to 0. And the idea is to look at this point z star, which is, so the vector c that I have is in Rn. So my z star will be equal to e to the t times c. And so let's say z star of t will be e to the t times c, and I'm going to let t go to infinity. Okay. So again, this is a vector version. So what I mean, okay, let's actually, the notation gets confusing. So z star of t is equal to this. So what I mean by this is that the ith coordinate of this vector is equal to e to the t times ci. Okay, so that's what I mean. Now once you have this, you can write P of z. P of z is equal to summation over all kappa, which are integer vectors, Cp of kappa z to the kappa, which is equal to summation again over kappa, Cp of kappa, e to the t times z star of t dot product the c vector. Okay. Now the point is, I know that the dot product of no, wait a second, sorry. What am I doing? Sorry, I'm not doing this correctly. Z to the, so this should, sorry, I want to look at, I want to look at P of Z star of T, okay? And this would be Z star of T raised to the K. And I'm gonna have e to the log of, log of Z star times kappa. Okay, so I'm going to get this. Good. And then this is equal to summation of Cp of kappa, e to the t, and then log of z star. No, sorry, I didn't need the t here. Log of z star is exactly t times c. So this is exactly e to the t c dot product kappa. And now the point is c dot product kappa is less than or equal to b, because kappa is a point inside the polytope or in the boundary of the polytope. So this thing is less than or equal to basically e to the t times b summation of Cp of kappa. And similarly, you can do z star to the alpha, which is equal to again e to the alpha dot product log of z star. It's equal to e to the t times alpha dot product c, and it's equal to e to the t times b plus epsilon. Okay. Now you see that the bottom one, so the top one has a summation of the coefficients, whereas the bottom one has this extra epsilon. Now, when you let t go to infinity, the summation of the coefficient remains invariant, but this t times epsilon goes to infinity. So the denominator will, go above the numerator, and this becomes 0. Okay. So yeah. So what I showed was that basically, if you're in the polytope, this is not 0. This is equal to 0, the infimum. Now, okay. So now let me tell you the main lemma, or the main theorem, which is that, okay, so now let mu be a probability distribution. Let me actually write it this way. Mu in 2 to the n. So mu is a probability distribution which maps subsets of 1 to n to non-negative reals. The distribution of subsets of 1 to n. And let alpha be in the Newton polytope of generating polynomial of mu. Okay. Then there exists an external field, lambda. There exists non-negative reals, lambda, such that if you look at this distribution, so remember we defined this distribution lambda star mu. So in this distribution, the probability of every set S is equal to mu of S times lambda to the S. Okay, so that's the external field you apply to your polynomial or to your distribution. So in this distribution, the marginal of any I between 1 up to n is alpha. In other words, probability of, if you look at this lambda star mu, the probability of I is equal to alpha. Well, okay. So what am I doing? What am I doing here? The point is I have one probability distribution mu. It has some marginal probabilities. Every element has some probability. But I'm not interested in that. I want to change marginal probability. But I don't want to change my distribution so much. What I'm saying here is that you can apply an external field to your distribution to change your marginals to any point in the Newton polytope. Okay, and the very important thing, the very important consequence is that if mu is strong Rayleigh, then so is lambda star mu. Okay, I mean, the point is, so far the strong Rayleigh distributions seem very limited, right? You could have just one distribution, right? But for example, we talked about uniform distribution over spanning trees. Now you may think that, okay, that distribution may not be ideal for many applications, because depending on the graph that you give to me, every edge has some marginal probability. For every edge, there is some probability that this edge shows up in a uniformly random spanning tree. But This may not be desirable for your application, right? In your application, you may want some specific distribution where maybe this edge is chosen probability 0.1, this other edge is chosen probability 0.2, and so on and so on. Okay, and what this is saying is that give me any point, as long as it is feasible. You need the point to be in the Newton polytope for it to be feasible, for it to be feasible to be marginal probabilities. If it is not a Newton polytope, basically by the previous lemma, there is no way you can get a distribution such that it has alpha as the margin. So give me any point in Newton polytope. I can basically change the distribution just by an external field, no more, nothing more. I can change the distribution, turn it into another distribution which has alpha as the marginal. Furthermore, the new distribution is still a strong Rayleigh. So you have all of the previous properties, all of the properties of real stable and strong Rayleigh distribution that we talked about. In addition, you have the ideal marginal vector. Okay, so that's what this theorem says. Any question?
So this lambda depends on the choice of alpha, right? So we have
exactly. Lambda depends on the choice of alpha. And I should say some more things. So first of all, you can find this lambda in polynomial time. I'm not going to discuss it here how to find. I will prove that it exists, but you can write a convex program. Basically, the point is you can use the convex program, max entropy convex program to find this lambda, so you can find it. There is one also tricky thing. I'm not going to get into it. In general, if you want to be, you have to be careful whether lambda is on the boundary of my polytope or is inside the polytope. If it is on the boundary, you may not get marginals of lambda exactly, but you can get arbitrarily close to it. So if lambda is on the boundary, you may want to push it a little bit inside the polytope and apply the same field. Okay, but I'm not going to get into those technicalities. So how do you prove such a thing? Basically, the proof is not so complicated. It's so let's discuss it. So first, I want to tell you how can you figure out the marginal of a distribution using the generating polynomial of that distribution. So let's say you have this distribution mu, and you want to figure out what is the marginal of I. Probability that if you sample a set S from mu, the probability that I is in S. I claim this is exactly equal to partial Zi of G mu when you evaluate it at Z equal to all 1. Why is that the case? First of all, if you evaluate G mu at all 1s, you get 1 because it's a summation of the probability of every set in the support, or in other words, because it's a distribution. Now, when I differentiate with Zi, I kill every monomial which doesn't have I. I only keep those that have I. And again, I evaluate it at 1. So I get the summation of weight or summation of the probability of the samples that contain I, which is exactly marginal of I. Okay. Now, there is one caveat. This definition assumes that, or this identity assumes that G mu is normalized, meaning that, so this assumes that G mu of all 1 vector is 1. Okay, so that could be okay. In general, we would like definitions which are sort of invariant under renormalization. So how can we change it into a definition which is invariant under renormalization? We can look at the derivative of the log. That's the idea. So look at partial Zi of log of G mu. This is equal to partial Zi of G mu over G mu. And now you evaluate it all once.
Oh, there is a question in the chat.
Oh.
Is it so? Maybe this
is it clear that lambda star mu sum up to 1, or will it appear from the choice of lambda? So the thing is, you can choose lambda to make sure that lambda star the lambda star mu add up to all 1. You can rescale lambda basically. Or if you want, you can just pick a lambda and then you can pick a lambda and then renormalize like the probability of every sample by summation of the probability of samples. But the thing is, when you solve the convex program, it will actually give you a lambda that everything adds up to 1. Okay. So good. So yeah, so if you look at the derivative of the log, you exactly get what you want. So you get to forget about the renormalization. You get the partial zi of g mu over g mu, and that's exactly equal to probability of I under this distribution mu. Okay. So in other words, to rephrase it, what we're interested in, we want to find an external field such that if you apply it, the derivatives of the log are exactly alpha. Okay. So now let's go back to this max entropy convex program that I started this lecture with. So recall the max entropy convex program. It was infimum. I'm gonna write the convex version of it. You have infimum of y log of p of e to the y1 up to e to the yn over e to the y times alpha. And alpha is in the Newton polyton. So this is a convex program. I'm going to write out the optimality condition of this convex program. So let's say y star, an optimum solution. And I want to write down the optimality condition. So I know that partial zi of log of p of e to the y1 up to e to the yn over e to the y times alpha. You can actually take the log and write this way. It's in fact equal to this minus y times alpha. Let's say this is, if you evaluate it at y equal y star, you get 0. Okay, so that's what optimality condition means. If you compute this at y star, you get 0. Now, what does this mean? This means that so let's take the partial. Let's take. Sorry, it should have been partial yi, not partial z. So let's take the partial yi of the thing inside. So partial yi, therefore, partial yi of p of e to the y1 up to e to the yn over p of e to the y1 over e to the yn. If you evaluate it at y equal y star, it must be equal to alpha. Okay, this is equivalent to the previous thing. Now let's understand this thing. So we have this identity, and we have this for all I. Okay. So what does this mean? Let's define this lambda, the external field that we're interested in, to be e to the y star. Okay. In other words, lambda I is equal to e to the y star I. Okay. Now here is the important fact. If I look at p of e to the y1 all the way to e to the yn, sorry, this should e to the y1 e to the yn evaluated at or y star, so y equal y star, which is nothing but p of e to the y star 1 all the way to e to the y star n. I'm saying this is exactly the same. It's exactly the same as p of lambda 1 z1 all the way to lambda n zn when we evaluate it at z equal 1. Just a case. Okay. Sorry. Sorry. I'm applying everything I said to g mu, not p. So there is no p in this theorem. All of these p is g mu. Just g mu. Okay. So all of these p is really g mu. Okay. So you get this. Now, similarly, you can rewrite the denominator. So in the denominator, we have partial yi of g mu of e to the y1 all the way to e to the yn, and you evaluate it at y equals y star. I'm saying that's also the same as partial zi of lambda 1 z1 all the way to lambda n zn, evaluated at z equal the all ones vector. Okay, it's the same fact. Now you put these together, you get that. So remember we had this identity above. So I'm saying it follows that alpha I is equal to partial zi of g mu of lambda 1 z1 all the way to lambda n zn over g mu of lambda 1 z1 all the way to lambda n zn, evaluated at z equal 1. Okay, and now this is nothing but the generating polynomial of the distribution where you apply the external field. This is exactly equal to partial zi of g of lambda star mu of z over g of lambda star mu of z, evaluated at z equal all 1. That's it. So in other words, all you need to do is to solve this convex program. Yes.
So please, may I suggest, if you have a question, because in the chat it can be overlooked, Shayan, would it be okay if people just unmute themselves?
Yeah, definitely. Please do. Yeah,
I think it's
when
better.
I'm writing down, I don't get to look at the chat. Yeah. So where do we use that alpha is in the interior of the polytope? We use it to say that this, if alpha is not in the interior of the polytope, as we proved, this max entropy convex program here will have optimum value 0, or sorry, this one would have optimum value minus infinity. So there is no really optimum point. You don't get to write down the optimality condition. Now, when it is inside the polytope, this optimum is achieved. This infimum is achieved at some z, and you get to write down the optimality condition. That's how you use it. Any other question? So again, just to summarize, to prove this theorem, to find this new distribution lambda star mu, all you need to do is to just write down this max entropy convex program and solve it, and find out the optimum y star, and just let lambda to be e to the y star. That's it. So I should say one more thing. It may not be trivial how you would solve this convex program. So first of all, this theorem I said, it has nothing to do with real estate polynomials. You can apply this theorem to anything, to any polynomial in general, and any alpha in the Newton polytope, as long as the polynomial has non-negative coefficients. So this theorem has nothing to do with real estate polynomial. The application had something to do with real estate polynomials. Now there is a difficulty if the distribution mu, or in fact the generating polynomial g mu, is not real stable, you may have difficulty computing the optimum of this convex program, because to calculate the optimum of this convex program, let me just mark it again. To calculate the optimum of this convex program, you need to be able to evaluate it. You want to use some ellipsoid method or interior point method. You need to be able to evaluate this convex program at a given point, y1 up to yn, and also be able to evaluate the derivatives of it. Now, if you have a real estate polynomial with non-negative coefficients, it turns out that yes, you can evaluate this polynomial at any point and its derivative. I'll talk about it in the 5th lecture. But in general, if mu is arbitrary, it may be NP complete or sharply complete to evaluate this polynomial. Good. So now the last thing I want to say in this lecture is applications to TSP. So applications to TSP. So if you're not familiar with traveling salesman problem, you have a list of n cities and their pairwise distances. And we want to find, so let's say we have a list of n cities, n, and their pairwise distances, let's call it C. C is from n times n to non-negative reals. The goal is to find this tour that visits every city at least once and comes back to the starting point. So there is a so-called LP relaxation for this problem, which is as follows. You say that I want to minimize summation of Cij Xij. So you have a variable for every edge ij in the graph. You want to minimize the cost subject to summation of j Xij is equal to 2 for all I, and summation of I in S, j not in S, Xij is at least 2 for all sets S, and X is non-negative. Okay, here this is really you have variables for every edge. Okay, so you should really put set around these guys, but okay, let me just slide that under the rock. So okay, so this is the so-called LP relaxation of TSP. It's very it's not hard to see that if X is an integer vector, let's say it comes from a Hamiltonian cycle, then all of these constraints are satisfied and you get a solution. Now you drop the integrality constraint, say that I'm happy with any non-negative vector X, and then you get this relaxation. Now, you know, the interesting question for TSP is that given a feasible solution, optimum solution to this LP relaxation, how would you round it to an integer vector, to a tour that visits every city at least once? Okay, I should say, you usually hear that in TSP you should visit every city exactly once. So if you assume that C satisfies triangle inequality, then you can basically turn any tour that visits every city at least once to a tour that visits every city exactly once by following a Eulerian sort of by shortcutting technique. But okay, I'm not going to get into that details. So let me let me tell you an algorithm based on this max entropy convex program. So before that, I need a sort of notation assumption. So let's say I have X0 to be an optimum solution of this LP. It turns out that without loss of generality, we can assume there exist two special vertices. Let's call them vertices n-1 and n, such that x of n-1 comma n is a 1, and c of n-1 comma n is 0. So there are two vertices at distance 0, and the x of the edge between them is 1. It turns out, okay, you may say that why should that hold? It's true that a given, this should be x0, okay. The given x may not necessarily satisfy this, but the thing is, if it doesn't, you can sort of blow up one of the vertices of the graph into 2 and put an edge of fraction 1 between them and cost 0, and sort of divide the edges from the original vertex in these two half and half. So you can sort of engineer your solution to look like this. Let's just assume it, and this is a simple technical fact you can prove. So once you have this, now you define X, so, sorry, let me first say one other thing. So let's say E0 is equal to, I'll call this edge E0. Okay, so let's say E0 is the edge n minus 1 comma n. So I define capital E0 to be the edge E0 union E. Okay, so E is all edges except the edge E0, and E0 is a special edge. This capital E0 is support of this X0. Now the point is, I'm not interested in this edge E0, I just want to drop it. So say X is the same as X0, but you drop the edge E0. So just forget about E0, look at the rest of the, let's look at the rest of the solution. Let's say X is that thing. So just one thing, the sanity check you want to keep in mind is that the degree of, or the so-called fractional degree of every vertex except n minus 1 and n in X is 2. N minus 1 and n vertex have degree 1, right? Because we dropped the edge E0. Now you have this X. It turns out that, so this is a simple fact to check, turns out that X is in spanning tree polytope of G equal V comma E. What do I mean by spanning tree polytope? This is so-called a matroid-based polytope. If you read the background notes on matroid, you can see the definition. I'm not going to define it here. Another way to think about it, spanning tree polytope is the Newton polytope of the generating polynomial of all spanning trees, of the spanning tree polynomial that we talked about. Okay, so X is in the spanning tree polytope, it's in the Newton polytope. Therefore, here is the interesting thing. But by everything we said so far, there exists an external field lambda such that okay. Actually, let me say one more thing first. Just okay. Let me first say assume. Okay. Assume mu is uniform distribution over spanning trees. Of G. Then there exists this external field such that marginals of lambda star mu are equal to X. So in other words, probability of every edge being in a tree sampled from lambda star mu is equal to X of E. Okay, so that exactly follows from everything I said. And this lambda star mu is a strong value distribution. Now the algorithm is very simple. The algorithm is that, okay, sample a tree T from lambda star mu, find mean cost matching, on odd degree vertices of T, and then return, find mean cost matching M, return T union M. Okay, so this is very, if you have seen Christofides algorithm, this is very similar to Christofides algorithm. The main difference here is that you sample your 3T from the so-called max entropy distribution, or this external field, which comes from a strong Rayleigh distribution. So you have a strong Rayleigh distribution spanning trees with marginals equal to X, equal to the feasible solution of the LP. You sample a 3T from that strong Rayleigh distribution, and then you add the matching on top of it. The theorem we proved recently, it's a joint work with Anna Carlin, Nathan Klein, is that this algorithm gives 3/2 minus some epsilon approximation for traveling salesman problem. Okay. So in the proof of this, many properties of these strong Rayleigh distributions become useful. So I want to tell you one specific lemma that we proved, but let me first say a simpler property. As I said, every vertex except these two special vertices n-1 and n, every other vertex has degree 2 in x. X of summation of x of edges neighboring to every vertex is 2. Now, you get this very nice property. You get to look at the degree distribution of a vertex. I know that the expected degree of any vertex except these two special vertices is 2. Right? The expected degree is summation of the x of e's neighboring of that vertex, which is exactly equal to 2. But what is the distribution? The distribution, as we proved in the first lecture, is nothing but summation of independent Bernoullis. So you have independent Bernoullis, and you know that the degree of every vertex is never 0, so it's always at least 1. So one of your Bernoullis is 1, and the other one can be anything. So you have these independent Bernoullis, which add up, which their success probability add up to 1. And you can study, and they exactly give the distribution of every possible vertex in this tree, in this graph. So in particular, one simple corollary is that for every I not equal to n-1 and n, the probability that dt of I, so dt of I mean degree of vertex I in the spanning tree T, the probability that this is even is at least 1 minus, sorry, it's about 0.43, so it's 1, I think 1/2 minus e, sorry, about 1/2 minus e to the minus 2, like that. Just double check, I said it correctly. 1/2 minus 2. No, I didn't say it correctly. 1 second. I'll figure it out correctly. Forgot, but it's about 0.43. So you can just simply get this by the fact that the degree distribution is sum of independent Bernoullis. So this is very much in contrast with, for example, what you would get by classical algorithms and TSP, which is like Christofiris. If you choose a minimum spanning tree in a graph, you could have many vertices of odd degree. In particular, you could have all vertices of your graph have odd degree, but here you get, almost half of them have even degree. Okay, this by itself is not enough. You need many more properties. So the more interesting thing I wanted to prove is the following. So here is a lemma which says that let V1 up to Vk be vertices which do not share edges. So you have disjoint vertices in the graph. Now probability that dt of V1 equal dt of V2 equal dt of Vk equal 2 is at least e to the minus k. So you give me any k vertices in the graph which do not share edges with a, I mean, think about k as some constant. With a constant probability, essentially, almost all of them will have even degree in the graph, in the tree. Okay, so it kind of acts as like independent. And this e to the minus k is basically the same as the e to the minus k of the Gurwitz's theorem. Okay, so let me very briefly sketch the proof of this, and then we'll be done for this lecture. So the proof is not so hard. So you do the following. Let's say you you define this polynomial p with k variables, y1 up to yk. I define it like that. I look at g of lambda star mu. So this is the generating polynomial of my random spanning tree distribution with marginals x. I look at g of lambda star mu, and I do the following. I set ze equal to y1 for all e which are neighbor of v1. Then I set ze equal to y2 for all e which are neighbor of v2. And ze equal yk for all e which are neighbor of vk. So here I'm crucially using the fact that these vertices do not share edges. Every edge in the graph is either, and also set z equal 1 otherwise. So every edge of the graph is either neighbor of one of these vertices or none of them. It cannot be neighbor of two of these vertices. Okay, so you get this new polynomial p with k variables, which is not any more homogeneous, but it is real stable. So p is real stable. Now, what we are interested in, so actually another way to write down p, I can write p of y1 up to yk as summation of all spanning tree t mu star lambda, the probability of this tree t, times the product of yi raised to the dt of vi. Okay, so this is exactly this polynomial. For every tree, you raise yi, the degree of that vertex, the vertex I, vi, in the spanning tree. Now, the goal basically is to say that I'm interested in probability that dt of v1 up to dt of vk equal to, this is exactly equal to 2 to the minus k. You take partial y1 squared up to partial yk squared of p, and you evaluate it at y equals 0. You want to say this thing is at least e to the minus k. I'm exactly interested in the coefficient of y1 squared, y2 squared up to yk squared. That's exactly the probability that all of these k vertices have two edges in my spanning tree. Okay, so how would I study that? The point is, I know that every vertex has degree at least 1 with probability 1. So I never have y1. I never have a monomial with y1 where exponent of y1 is 0. The exponent of y1 is always at least 1. So I can factor out y1 up to yk. I can write p as y1 up to yk times q of y1 up to yk. Right? Because every vertex has degree at least 1. So I can just factor out a monomial y1 up to yk and just look at q. So now I'm interested in the coefficient of y1 up to yk in q. I want to say this is at least e to the minus k. Okay. Now everything is very nice. Q is a strong Riley, or sorry, Q is real stable. This is exactly a special case of Gurwitz's theorem. So all you need to say, is that, so by Gurwitz's theorem, enough to show infimum of y, q of y over y1 up to yk is at least 1. If I show that, then I'm done. This e to the minus k, it just comes from the fact of k variables. So that's all I need to say. I'm out of time. Let me not prove this. You can read the proof of this in the notes. But this basically simply follows from the fact that v1 up to vk have degree 2, expected degree 2 in the tree. Okay. So anyway, so yes, that's what I wanted to say, is that this Hurwitz's theorem, which originally was talking about permanent and etc., now it can be used in a probabilistic context, and you can use it to talk about the probability that the number of vertices have degree equal to 2. This theorem that I said, you can actually generalize it. The theorem. This lemma that I said, you can generalize it much further. You can say, for example, it doesn't have to be vertices. It could be sets of edges which do not intersect. And here I crucially use the fact that the expected degree of all of these vertices is 2. You can also tolerate that. You can say if the expected size, you can have sets of edges which do not share edges. And you can say if the expected number of edges I get in these sets is basically close to 2 or close to an integer, then the probability that all of them are exactly equal to that integer is a constant. So if you want to see the exact formulation, maybe I talk about in the next, I probably don't have time to talk about in the next lecture. You can look at the last theorem, theorem 3.6 in the notes. I stated that formulation, and in the assignments we will sketch the proof of this theorem, the more generalization, the more generalized theorem. Okay, let me stop here. Let me know if you have a question.
Okay, so thanks, Shayan. That was a very surprising. Okay, yeah, it's impressive. Are there any questions? Okay, so thanks, and we all meet at the exercises or tomorrow for Subhash's and then Shayan's lecture. Okay, bye bye everyone.
Thank you. Bye bye.